let's start this with just understanding the Coriolis force. All right. So first of all, it's not a real force, although on Earth it certainly appears by that it's a real force. So here's why it's not a real force. All right. So let's say you have two kids sitting on this this platform that has the ability to rotate. All right. So that's it's like a little merry-go-round type thing. Right. So the two children are rolling a ball back and forth. And while the platform is not rotating, the ball just follows a nice straight path from one child to the other, one child to the other. Okay. So that's just, normal Newtonian physics, right? It's basically what Newton taught us about the world. But Newton also realized that if these two children were on this platform, and the platform was spinning, let's say, for example, in this particular case, the platform is spinning in a counterclockwise manner. Okay, so what's good about that, of course, is because that's the same direction that the Earth spins. All right, so we're spinning counterclockwise. And so this child in the red shirt rolls the ball just like before, but because they're on a spinning platform, and they're spinning in a counterclockwise direction, the ball will be deflected to the right. As it rolls along, it'll be deflected to the right, and that deflection is just because their reference frame is actually spinning, right? So there's no actual force that causes this ball to roll to the right. It's just the fact that it's actually going in a straight line, for what would be a straight line for itself, but it can't be a straight line because the ground, if you will, is moving, right? So between the two children, the ground, as the ball is making its way to the other child, the ground has moved. Well, the table, whatever the merry-go-round that they're on has moved, and so it appears as though the ball is deflected to the right, and so that idea is called the Coriolis force. And by the way, that would be in the northern hemisphere, it would deflect to the right. In the southern hemisphere, it deflects to the left. And so that's the idea of the Coriolis force. All right. So I want everybody to understand that it's not some mysterious thing. It's just because the Earth is rotating. That's all that's about. And that affects the wind. Okay. So here, let's go back to this. Let's see. Let's go back to where we were. Yeah. We were back a little further than that. Sorry. We're really far back here. All right. So I think I was right here in the last video. All right. So let's go on to that. All right. So that I just wanted to explain this idea of the Coriolis force. So the air in the northern the atmosphere in the northern hemisphere will deflect to the right. It'll tend to, and by the way, the deflection is greater towards the poles than it is, and in fact, it's almost non-existent at the equator, right? And the other thing is, of course, in the southern hemisphere, the deflection is to the left. All right, so the deflection of the wind varies according to the speed and the latitude. So again, the greater the more you are towards the poles, the more deflection you see. Let's see. Oh yeah, I just said that. So, all right. Factors that influence the wind: the pressure gradient. Air moves from higher pressure to low pressure. Don't forget that. And remember that the higher pressure is when you have hotter air, right? I'm sorry, that's just the opposite. Yeah, you got to think about that sometimes. The higher pressure is oh, you know, I was right. Sorry, the higher pressure is higher temperature air, right? Because the air molecules are put are when they're heated, they're oh no, jeez, so sorry, I got that wrong. So let me try this again. Sorry about that. All right, so higher pressure air is when the air is cooled, right? So the air, why is that? Okay, when the air is cooled, the air molecules can get closer together, and when they're closer together, that's higher pressure. When they're heated, they spread apart more, right? And so that's lower pressure. So higher temperature leads to lower pressure, and we're assuming that the air, these parcels of air are not mixing with other parcels of air, which is certainly not true. These are ideal situations to help us understand what's going on in the atmosphere. All right, so let me make sure we get this right. Right, higher pressure is due to lower temperature, and then lower pressure is due to higher temperature, right? Because higher temperature, the molecules move further apart, and so you get lower. All right. So the Coriolis force, it's still called that, or sometimes it's actually called the Coriolis effect. So it's fine. It's. I mean, on the surface of the Earth, you definitely see this Coriolis effect. So it's the apparent deflection of winds due to the Earth's rotation. So remember, in the northern hemisphere, these winds are deflected to the right. In the southern hemisphere, they're deflected to the left. And then you get this frictional force. The air moves close to the ground and encounters friction, of course. Right? All right, so this is just kind of showing what happens to the high pressure air and the low pressure air. All right, so and see, as I mentioned before, normally, not normally, but if the Earth were not rotating, you would have the hot equatorial air rising and then falling, but it wouldn't fall until it got to the north or south poles. But see, because the Earth is rotating, you get this. You get these. Actually, there's a total of 6 zones of circulation. So the first one is from the equator to a latitude of about 30 degrees, roughly 30 degrees north, and the same thing in the southern hemisphere. 0 to negative 30 degrees south, and so if you think about what is going on as far as where this air, this current, these two currents, where they rise and then they begin to fall at 30 degrees. So at 30 degrees, you think about what land masses are at positive 30 degrees and at negative 30 degrees. And those are the great deserts across, the Sahara Desert, the Arabian Desert. In the southern hemisphere, there's and also the Mojave Desert in California. And then in the southern hemisphere, of course, there's a huge desert in the middle of Australia, which corresponds to negative 30 degrees, right? So these deserts are due to this really it comes from the Coriolis force, right? And then between 30 and 60 degrees, that's where you get the next convection cell, and then there's another one between 60 degrees and the North Pole, and then negative 60 degrees and the South Pole, right? And so let's talk about what's taking place. This, of course, this from 30 degrees to 60 degrees, you're covering, most of the United States. And so what you have, because of the but because of the Coriolis force, you have what are called the westerlies. And what we mean by that, this is the prevailing wind that goes from the west. They're called westerlies because they're going from the west towards the east. And that's not always the case, but the average day, you just look at the weather, for example. Usually the weather is coming in, for us here in South Carolina, it's coming in from Georgia, or Tennessee, and, heading towards the North Carolina mountains. And then it gets to us here in the upstate. So it's usually whatever's going on in the west first, and then it gets, for us, it's in the southwest. What's going on in the southwest crosses the country and then eventually ends up as our weather. Of course, the Appalachian Mountains have a lot of effect on that, but it's the overall motion, is this westerly motion that takes place. All right. And of course, you think about, hundreds of years ago, when humans began to sail the oceans, they knew about these, between 30 degrees and 0 degrees, where the equator is, there were these, the trade winds that went from easterly, right? So they were going from the east towards the west, right? So if you were in Europe and you wanted to cross, you could take this path, and then if you wanted to go back, you would make sure you're above 30 degrees, and you're sailing, right? You're actually using the wind, and it makes things a little easier. And this is what's called the doldrums. The doldrums. The doldrums are when sailors got right around to where the equator is, the sails wouldn't fill up, or very rarely would they fill up, and so the ships wouldn't go anywhere. It would take a long time to get any wind at all. I mean, sometimes they'd get some wind, but not as much as if you were in the trade winds or you were in the westerlies. All right, so that's all comes from this idea of not the idea, the fact that the Earth is spinning, and so there is this Coriolis force. All right, so I talked about the deserts. All right, so at the equator, the rising warm, moist air creates a zone of low pressure. All right, so that's this low pressure right here. It rises, and of course that's what they call the doldrums. So that's really close to the equator. You get that, and then you have from about 30 degrees north or 30 degrees south to about 60 degrees, either north or south, correspondingly. You'll get these westerlies. I'm not really going to go into why they call that the horse latitude. That's just gross. All right. Anyhow, yeah. And then above that, from 60 degrees to the poles, you get the cold air meets the dry warm air meet. You get cool dry air meeting warm moist air, and so you have these polar fronts. All right, so here, let's answer some of these questions. The prevailing westerly winds are affected by the Coriolis force, and it deflects winds. So to the right in the